Last time we had started Explorations with Patterns, section 1.2, and we had taken a look at two sequences in depth. Those were arithmetic, which means you add a term to get to the next term, and geometric, where you multiply by something to get to the next terms. And we talked briefly about a third sequence called Fibonacci sequence, and that's kind of where we got to last time. I'd like to start back in on example 3. Example 3 talks about one of our definitions from the first part of this lesson, or maybe last lesson, I can't remember. I think it was this lesson, though. The word counterexample. It says to find a counterexample for the following. If n is a natural number, then n plus 5 divided by 5 is equal to n plus 1. So if you remember, a counterexample means an example that shows something is not true. So in particular, what you're looking for is a number that you can choose for n, where these two sides of this equation are not going to give you the same value. So can someone give me an example of such an n? 5. So if n is equal to 5, let's see what happens. On the left-hand side, we get 5 plus 5 over 5, which is 10 over 5, or 2. And on the right-hand side, so this is our question mark, is are these equal? I have 5 plus 1, which is 6, and these two are definitely not equal. And the reality is there's a lot of numbers that I could pick that would actually make this particular one false. Sometimes when you're doing counterexamples, there's only one thing that makes it false, and it's harder to sort of find that one value that won't work. But on this one, there's lots of values that won't work. So looking at this particular thought, right, that n plus 5 over 5 is equal to n plus 1, what reason might you speculate if a student thought this was true? What would they have done to come up with this error?
No, would it be like 5 times n divided by 5 could have been?
Okay, yes. So what are they doing with this problem specifically to arrive at that kind of a conclusion?
They're adding like at the top. Is that?
I don't think so. I think you've got part of what we want to talk about, but you're not got the first part yet. Any other thoughts as to what they're doing? Yep. Yeah, so they're reducing just this part, right? Just the 5 over 5 part, and they're sort of ignoring that the 5 is also underneath the n. Do you guys see that? So they're doing some sort of incorrect reducing. So they're incorrectly reducing. You can think of it as ignoring that they never divided by the n by 5, right? They don't divide n by 5. One of the things Michaela mentioned is that they're treating it like it's multiplied, right? Like if we had 5n over 5 and we were able to reduce these 5s, I think that's where you were headed from, right? And that would leave us with 1n or just n, right? That's how they're sort of treating it. They're treating it very much like it's a multiplication fact instead of an addition fact. And of course, it simply doesn't work for addition facts. One of the things that it would be worth showing the student is that if it doesn't ask this particular question, but sometimes you're asked questions like, what would you say to the student who did this? Your book likes to ask that question. It would probably be a good idea to show the student that 5 like this is equal to n over 5 plus 5 over 5. So you're separating the fraction back into its individual pieces so that this is actually equal to n over 5 plus 1, not just n plus 1. And while you can show lots of counterexamples that show the other one doesn't work, you could also show lots of examples that show that this one does, to kind of give a feel for the fact that real numbers make this work, whereas real numbers make the other one not work. So those are all good ideas on how to think about why this problem doesn't work that way. All right, here's something very interesting, and you may or may not have heard of these before. There are numbers that are called figurate numbers. So these are based on visually geometric patterns. These examples are neither arithmetic nor geometric, and they can be represented by dots arranged in the shape of certain geometric figures. So I would like to show you several, well, two specifically today, examples of figure eight numbers. So the first one we're going to look at is a triangular number. So give yourself some space underneath the dots you're about to create to write numbers when we're done. So the first pattern in my sequence or whatever, the first term in my sequence is 1 dot. The second one looks like this. The third one looks like this. The fourth one looks like this. And of course, my pictures aren't perfect, but I think you get the idea. And visually speaking, it looks like a triangle. So these are called triangular numbers. Okay, that's it. They're called triangular numbers for that reason. If we looked for a numerical pattern here, what it's referencing is how many dots there are. So for example, there's 1 dot here. There's 3 dots here. What would come next? 6, 10, right? And could you continue this pattern if you were asked to draw the next 2 dot arrangements? Or could you continue the pattern if you were asked to find the next 2 terms in the sequence, just the numbers? You could, right? Each time it looks like you're adding an additional row along the bottom and sort of shifting it up and adding a new row, right? Yeah, and I'd like to show you something else that happens very interestingly with this, and it happened last time with an example we came across as well. It tells you right here that these are neither geometric or arithmetic, right? They don't follow that pattern. But there is a pattern in the numbers themselves. So let's actually write these down. I have 1, 3, 6, 10, just because I want one more term because it'll make it easier to see. Give me one more. What do you think would happen after 10? It's 15. Okay, so we did this last time where we said, okay, it's not arithmetic, it's not geometric, I can't multiply or add to get the next term, but I can look at what would happen if I tried. So like on this one, I'd have to add 2, and then I'd add 3, and then I'd add 4, and then I'd add 5. So it's not arithmetic because these don't all match, but you do see that they create a pattern, right? That if I did it a second time, what would happen? They're all 1s. And that second time that I do that is called a second difference. Yeah. So this is a second difference problem. If we were to be able to do so, again, this is not in the realm of what we're doing, but this would be created as an x squared or an n squared kind of pattern because it's a second difference. I mentioned that last time. So figure eight numbers have the ability to do this second difference problem, at least on this one it did, on the triangular numbers. I have one more that I want to show you, and these are square numbers. Okay, so dots again, right? So do 1 dot, and then we're going to do this shape. That shape. I suspect you could tell me what the next shape should look like. What's this supposed to look like? A 5 by 5. Yeah, exactly. Good. All right, so if I were to create numbers to represent these, what would they be? 1. Yeah, and I bet that you actually know what that general term should be. It's n squared, flat out. Yeah, this actually is a pretty straightforward, and again, I'm not going to ask you to do it, but it's n squared. Definitely is. And if you were to go ahead and look at that same first differences, second differences business that we did on the last one, I'll do 25 as my last one just to give us a little bit longer to go with this. You'd see that this is adding 3, 5, 7, 9. Again, not arithmetic, but there is a pattern because if I did it a second time, they have a common second difference, right? They're all plus 2s. All right. We talked last time about two different types of reasoning, inductive and deductive. Do you remember that? Inductive reasoning means that we start out with some kind of a pattern and we create generalizations. Right? We say, this is what I expect to happen every time. Look, let me tell you, this morning when Alexa told me that it was supposed to be 69 degrees, I made a decision about what to wear. And this is not making me happy outside right now, right? And I'm very grateful that no child in my house asked me, Mom, can I wear shorts? Because I would have said yes. None of them tried, and really glad, because they would have been really cold at recess, right? That would have been bad. So this is making a generalization, a pattern based, or making a generalization based on patterns. The last few days have done this, and now I expect this to happen. And that's what weather forecasting, for the most part, is, as well as looking at patterns of behavior. So take a look at this particular example. This is a real life thing that happened, by the way. In the fall of 2011, the newly formed Hurley College of Science and Mathematics, which is what the math department is housed in here at OBU, was created, and we had a meeting. On the board, the dean had written the value 3.1415 ... was written, and we were asked to find the next two terms of the sequence of numbers. All right. So your role right now is to write down what you believe the next two terms in the sequence should be and why. So take 30 seconds, write down what you think the next two terms should be and why you expect that to be the case. Okay, somebody offer up for me what you believe the next two terms would be. 1, 6. Okay, so one possibility is 1, 6. How many of you said 1, 6? Just raise your hands. Okay, about 2/3 or 3/4 of the class. Anybody give another option? 9, 2. How many said 9, 2? Okay, were there any other options that people came up with? Okay, so the question is, what happened? Well, most of you probably went with the 1, 6 because you're thinking about patterns the way that we've been looking at patterns in this particular section of material, right? Yeah, we've been looking at sequences and how comparisons and things like that. So in that room that day, in the science and math department, nobody said 1, 6. Because what were we doing? Michaela? What is the 9, 2 from?
Pi.
It's pi. It's the next two digits in the expansion of pi. So let me ask the question one more time. Why would that have been where all of your science and math professors went?
Because they go with pi more often.
Because we work with pi, right? It's just something that we see so much more frequently than analyzing distinctive digits in a particular pattern of numbers, right? That's what I did. I looked at it and was like, well, it's 9, 2, obviously. What a dumb question to be asked. I mean, that's what I thought when it was happening. And you guys thought the same thing. Well, it's 1, 6. Obviously, what a strange question to ask, right? So what I want you to take away from this particular example is this next question. It says, what does this tell you about inductive reasoning? What it should tell you, and I'll let you write this in your own words, but what it should tell you is that inductive reasoning doesn't always come out with the same answer from different people's perspectives or different perspectives of the problem. Sometimes there's more than one legitimately expected answer. And that's exactly why the dean at that time did this, is because she fully expected us to put down 9, 2, 100% guaranteed. So when she put up 1, 6 as another option, we all went, oh, that's a different perspective that I hadn't considered, right? So thinking about things from different perspectives. And for our purposes, the idea is that inductive reasoning doesn't always draw the same conclusions from one person as it does from someone else. All right, so the good news is that's it for today. And you guys have 30 minutes to actually take a look at your group work for this. If you do happen to get done early, yay. If it takes you a little bit longer, that's good too, because we actually have some time. So go ahead and we will get into groups now.